All right, this video is for section 4.5 and 4.6 in AP Calculus AB. We'll be finishing up chapter 4 here. This will be the final video for that chapter. So up to this point, we've put in a lot of effort into understanding how to evaluate indefinite integrals using either the chain rule pattern or U substitution. And so today we're going to take a look at a couple of examples that involve similar situations, except these will be definite integrals. You'll notice if you look at our first example here, there are limits of integration. In this case, a 0 and a 1. We'll be talking about how to deal with those sorts of situations. So this is what we did in class. For those that were absent, I hope that this helps you. So as mentioned, we've only worked with indefinite integrals only. We're going to be working with definite integrals here. What we're going to be doing is we're going to be converting everything over to U's, and we're not going to go back. We're going to leave everything in terms of U as we finish with these definite integrals. With the indefinite integrals we did before, we definitely had to plug back in the expression for x. If you look back in your notes, you'll see that that's really all we've been doing. Okay, so with these definite integrals, here's what we do. We will, just like before, we will always make the U the inside part of the composite. So in this case, the inside part of the composite is right here. It is x squared plus 1. So I'm going to make my U x squared plus 1. And then as typical, we find our du. So du would be 2x dx. And then again, typically we solve for dx. So we'd get du over 2x is equal to dx. Okay, so I'm going to go back over here and start trying to substitute. I'm going to leave my limits of integration off because those are going to change here in just a minute. I'll leave those off for now. So I know that u is equal to x squared plus 1, so I'm going to substitute that in for what I have highlighted in red here. It's going to be u cubed. But I still have the x and I still have the dx in here. I'm going to now replace the dx with what dx is equal to. And we know from over here that dx is equal to du over 2x. So in place of that dx, I'm going to put du over 2x. Of course, the x's will cancel like that. And so I end up with the integral of u cubed du. Instead of writing du over 2, I'm going to write the over 2 out front as a 1/2. And now I have to deal with the limits. The old limits were 0 and 1. And I'm going to calculate my new low limit. My new low limit, when I say low, I'm not talking about numerically lower, I'm talking about physically lower. So the old low limit was 0. So the way that I get my new low limit is I use my u equation with that. So I'm going to say u equals 0 squared plus 1, which of course is 1. And then in my new high limit, I'll do the same thing, except I'll use my old high limit, which was 1. And I'm going to get u equals 1 squared plus 1. And of course, that is 2. Now I'm ready to find my antiderivative, use FTC1, and finish. So 1/2 times 1/4 u to the 4th, evaluated from 1 to 2. Simplifying just a little bit here, I get 1/8 u to the 4th, evaluated from 1 to 2. At this point, though, I need to do my FTC1, so that would be 1/8 times 2 to the 4th, minus 1/8 times 1 to the 4th. So 2 to the 4th is 16, 1/8 of 16 is 2, 1/8 times 1 is just 1/8. So 2 minus 1/8 is 15/8. That's my final answer. Again, please notice that at no point did I plug the x squared plus 1 back in for the u. Because this is a definite integral, I'm going to leave everything in terms of u and just finish with that. It'll give me the same answer regardless whether I plug back in or not, but this is in most cases, the faster way to handle these. All right, so we're going to move on now to number 2. Okay, so with number 2, I invite you to do as much of the substitution as you can on your own. Watch the video to help you out, see how you're doing. But as always, we're going to make our u the inside function. So u is equal to 2 minus x, and du equals negative dx. And like we did before, we're going to solve for dx, would be negative du equals dx. All right, I'm going to go ahead and do my limits now. So my new low limit, again, this is talking about the location, not the value. So the new low limit, the old low limit was 1, so the new low limit is going to be u equals 2 minus 1, so that's of course 1. And my new high limit, u equals 2 minus 2, which is 0. So 1 is going to be the physically lower limit, 0 will be the physically higher limit. So I'm going to go ahead and start substituting. So when I do that, I get integral from 1 to 0. I've got this x minus 1 hanging out right here. In place of 2 minus x, or square root of 2 minus x, I'm going to write u to the 1/2. And then I know that dx is equal to negative du, so I'm going to write that as du in here, and then I'll put the negative on the outside. So this is the part that's a little challenging, figuring out what to do with that x minus 1, because if you're honest about it, you've got to realize that that shouldn't be there at this point. So the way that we handle that x minus 1 is by taking our original u equation, solve for x. So it's going to be 2 minus u equals x. So then I'm going to take that and plug that in for x in the x minus 1 factor there. So it's going to be negative integral, let's try that again, negative integral from 1 to 0, and in here it's going to be 2 minus u minus 1 times u to the 1/2 du. Okay, so if you're like me, you're a little uncomfortable with the whole integral from 1 to 0. We're used to that physically lower limit being actually the lower number. So I'm going to go ahead and do that. I'm going to flip those limits of integration. And again, I'm allowed to do that if I change the sign out front. So it would be positive integral from 0 to 1. And then in here, of course, 2 minus 1 is 1. So we'd get 1 minus u times u to the 1/2 du. Okay, so if you remember from before, the integral of a product has the potential to be challenging, and this is going to be one that's not going to work very well unless we eliminate the idea of a product here. So to change this from a product into something that's not a product, I need to distribute. This is a common thing. Please don't shy away from this. This will happen a lot, and it's important that you do it right. So it's going to be the integral from 0 to 1 of u to the 1/2 minus u to the 3/2 du. Don't forget to add your exponents when you multiply. Be very careful with that step. Seen that messed up before, so please do be careful. Okay, now I'm ready to find my antiderivatives. So when I do that, I get 2/3 u to the 3/2 minus 2/5 u to the 5/2. That's evaluated from 0 to 1. So when I try to do FTC1, I get 2/3 times 1 to the 3/2 minus 2/5 times 1 to the 5/2 minus, and if you think about it, plugging in a 0 is just going to be 2/3 times 0, which is 0, and 2/5 times 0, which is just 0. So that whole second term is just going to be a 0. So finally I end up with 2/3 minus 2/5 when I multiply those out. And getting a common denominator would be 15. So I think it'd be 10/15 minus 6/15. I'm coming up with 4/15. Once again, please notice that we converted everything that had to do with an x. We converted it over to being a u. And we left it there. We finished with that, and we got this numerical answer of 4/15. All right, so moving on, let's take a look at our next section. Okay, we'll take a brief look at how to integrate when you know that a function is either even or odd. Let's do just a basic review of a couple of key ideas with even and odd. Even functions are symmetric with respect to the y-axis. So a nice example of an even function is this parabola right here, f of x equals negative x squared plus 4, where if you were to graph this, it would look something like that. So hopefully you can see it. Can you see the y-axis symmetry there? I hope you can. If you just think about the y-axis as being splitting it in half, you can see that each half would be a mirror image of the other. So if I were to tell you that the integral from negative 1 to 1 is 22/3, that would be this area right in here. So if I told you that that area was 22/3, then what is the integral from 0 to 1 of f of x? So, of course, what I'm doing there is I'm taking this interval that I had before from -1 to 1, and now I'm splitting it in half from 0 to 1. So wouldn't it stand to reason then that the area would be exactly half of what that whole interval was? And hopefully that makes sense. So half of 22/3 is 11/3. So general principle, the integral from -a to a is equal to 2 times the integral from 0 to a. This holds true if f is an even function. All right, next we'll look at odd functions. Okay, so odd functions are symmetric with respect to the origin. So a good example of an odd function would be sine of x. I'll do my best to sketch in sine here. Sine would look about like that on the interval -pi to pi. So if I told you then, right here, that the integral from 0 to pi of that function was 2, so we're talking about this area right in there, then what would you guess the integral from -pi to pi would be? Well, because now you've got some area below, that area is actually going to end up canceling out with the area above. Because of the symmetry, the two loops are exactly the same size and exactly the same shape, and so they would cancel out. So if this is a +2 area, this would be a -2 area. Therefore, the entire integral from -pi to pi would equal 0. So a general principle, if g is an odd function, then the integral from -a to a will always be 0. All right, we'll look at one final section here, section 4.6. All right, so in section 4.6, we are going to look at one final way to approximate an integral using area under the curve. In the past, we looked at right sums, left sums, and midpoint sums. Those are all using rectangles. Now we are going to look at how to approximate the area under a curve using trapezoids. So a trapezoid is that old shape from geometry where two sides or one pair of sides is parallel, and we can use that to approximate the area quite well. As you look at a picture like this, you can see that those purple trapezoids do a pretty decent job of approximating the area under a curve with very little error. So two challenges involved with this. One of them is going to be to remember the area formula for a trapezoid, and the other is going to be a challenge to look at the orientation of the trapezoid, how they're positioned on the paper. So I hope you can see that, here you've got 1, 2, 3, 4 trapezoids. We're going to try to break them down, as far as their parts and how to work with them. One reminder, one thing to think about, back in geometry, we typically looked at trapezoids oriented like this, where the two bases were horizontal and the height was vertical. So in geometry class, you would have looked at this and called this the height. Maybe you would have called this base 1 and this base 2, maybe something like that. And if you look carefully at the way these are oriented on our paper, the way these trapezoids are used to approximate area, they're a little different, right? So if you look, they've been rotated 90 degrees. So it's almost as if this trapezoid that we're used to seeing has been rotated like this. So now it's kind of standing on its height. So if we were to look at these trapezoids, this would actually be the height of the little trapezoid, and maybe this would be base 1 and this would be base 2 or something like that. This would be another height right here, another base, a height, and a base. And so what's odd about this, of course, is that the heights are measured horizontally and the bases are measured vertically. So it does feel a little bit different because of the way the trapezoid is written, but it's still going to be the same area formula. And that area formula is, area of a trapezoid is going to be 1/2 times the height times base 1 plus base 2. So that is a formula that you do need to have memorized. So please make the effort to do so. You'll get some repetition with it here in this video. But something you got to have ready to go when it comes time for quizzing and testing. Let's go ahead and take a look at our one and only example here. Okay, so a certain function f of x has values given in the table below. Approximate the integral from 2 to 17 using trapezoids. So sometimes it's handy to sketch a picture of a graph like this that's presented as a table. So I'm going to do that for a couple of these. So here's my y-axis, here's my x-axis, and so my first point is 2, 3. we're going to say that that's, right about here. And then 3 comma 4, a little higher over there. 5 comma 8 would be maybe something like this. And then 8 comma 17, up here somewhere. I'll do right there, how about? Okay, so if I'm going to do some trapezoids here, I'm going to make a trapezoid for every interval. My first trapezoid would actually look like this. This was, down here, this was x equals 2, this was x equals 3. I'm going to try to find the area of that trapezoid. So here we go. I'm going to say integral from 2 to 17 of f of x is approximately, I'm going to find the area of that trapezoid, so it's going to be 1/2 times the height. The height is going to be the difference between 2 and 3. So the height is going to be this little measurement right there. And so the difference between 2 and 3, of course, is 1. And then the bases are going to be the 2 y values. So in this case, it's going to be 3 plus 4. So that is trapezoid number 1, the red one. Trapezoid number 2 is going to be right here, like that. So the x coordinate over there on the right was 5. So this is going to be plus 1/2. This time the height is not 1. The height is the distance between 3 and 5. Of course, that is 2. And then my heights are going to be the y values up here. So 4 plus 8. And I've got my purple trapezoid. Okay, so I'll do another one here. This final one on my graph at least is right here. It's a little bit steeper yet. This x value over here was 8. And so as I start to write out my area formula, it's going to be plus 1/2 times a height of 3, because the difference between 5 and 8 is 3. And then my bases are going to be 8 plus 17. Okay, so we have 3 more trapezoids to go. I invite you to continue on with the graph if you need to, or if you're starting to get the hang of this, you can certainly just use the table. Feel free to pause the video, try it on your own. I'm going to continue on here, but I'm just going to use the table only. Okay, so my next trapezoid is going to be going from 8 to 10, so it's going to be 1/2 times the height of 2. My bases are going to be 17 plus 30 plus, let's come back down over here. My next trapezoid is going to be from 10 to 12, so that's going to be 1/2 times a height of 2, because again the difference between 10 and 12 is 2. Then we've got, that should be, oh goodness, that should be 17 plus 13. I think I mentally added those. There we go. So it'd be 13 plus 9 for this one. And then finally, I'm going to do the trapezoid going from 12 to 17, so it'd be 1/2 times 5 times 9 plus 3. Okay, at this point I've got all my trapezoids, and I just need to work on multiplying and adding. So let's see here. It ends up being, let's see here, 3.5 plus 12 plus, see here, that's 75, so 37.5 plus 30 plus 22 plus 30. All right, I think that's good. Let's see here. That's 41, 53, 80, so that's 135. I think we're good there. Okay, so a chance to practice some of those hopefully is good. Make sure you've got that trapezoid area formula memorized, and I hope you find good success on this. I will see you in class next time.